Well, we're almost done with our look at techniques of integration, and to finish off our look at techniques of integration, we want to take a look at these things called improper integrals. So what makes an integral improper? Well, there are two things that make an integral improper. I will illustrate both of them here. One of them, so let's pretend that you have some function, maybe it looks like this, and you want to know the area from this number a all the way forever. So you would write the integral from a to infinity of f of x dx. If one of your limits is infinity, then the integral is improper. But that's not the only way for the integral to be improper. Let's pretend that you have some function like this. It's not hard to imagine a function like that. We know plenty of them. And we're interested in figuring out the area to the left of b, but to the right of this vertical asymptote. The integral from 0 to b of f of x dx is improper because there's a vertical asymptote in our interval of integration. One of the limits happens to be, it doesn't matter if it's a limit or not, there's a vertical asymptote that's part of our interval of integration. So if that happens, then the integral is considered improper. So how do we handle this? How do we handle this? In the first case, the integral from a to infinity of f of x dx. What do we do with that? How do we define that? Well, what we do is we find the integral from a to b, because we know how to do that. We know you take an antiderivative, you plug in, you subtract, except that we let this b be a generic b. This is a specific number a, this is a generic number b, and we take that generic b and we take the limit as b goes to infinity. So in other words, you have your function, I'll stay with the color coding here, and you have some a, you want to go all the way out to infinity, but you can't. So you go out to b, and then you push b. You take b and you push that to infinity, and as you push b to infinity, you get the area that you're looking for. A little bit of vocabulary. If the limit exists, then we say that the integral converges. And otherwise, the integral diverges. So that's vocabulary. If we take that limit and that limit is a number, then we say that the integral converges. And if we take that limit and that limit is not a number, then the integral diverges. And I can illustrate this with a few examples. Let's find the integral from 0 to infinity of e to the negative x dx. So we're clear. This is e to the negative x. This is the area we're looking for from 0 all the way out to infinity. We're going to figure out the integral from 0 to b, and then we're going to push b. That's the plan. So we're going to take a limit as b goes to infinity of the integral from 0 to b of e to the negative x dx. This is the function in play. This is the thing we're pushing. So we have to ask ourselves questions like, what is this integral? Well, how do we do that? We take an antiderivative of this thing, and we evaluate between 0 and b. Antiderivative, subtract. So what's that? Well, we sub in, so that's negative e to the negative b, negative e to the negative b, minus sub in the 0. So what happens to this thing as b gets large? Well, as b gets large, this goes to 0. And you're left with negative negative 1 over 1. Negative negative 1 over 1, that's 1. So all of this area forever is 1. What does that mean? That means that I can make the answer as close to 1 as I like by taking b further and further out. I mean, we never get to infinity, so it never is 1, but I can make it as close to 1 as I like just by going far enough out. I will demonstrate again. Integral from 2 to infinity of 4 over x cubed dx. So this is 4 over x cubed looks something like this. Here's 2. We want to go this way, so we take the integral from 2 to b, and then we push b. So this is the limit as b goes to infinity of the integral from 2 to b of 4 over x cubed dx. So we ask ourselves how you do that. Well, we take an antiderivative from 2 to b. What's that antiderivative? Negative 2x to the negative 2. Then the b goes in, and the 2 goes in, and we ask ourselves, what happens as b gets large? As b gets large, this goes to 0, which leaves us with negative negative 2 over 4. That's a half. And we've got it. So all of these turn out to be numbers? He asked in a foreboding tone as if it wasn't that way. By the fundamental law of classroom examples, this one isn't like the others. Well, how do we do this? Well, to be clear, this is 1 over x. Here's 1. We want that area. We can't find that area, so we go to b, and then we push b. This is the limit. B goes to infinity of the integral from 1 to b of 1 over x dx. Well, what's that? We take an antiderivative from 1 to b. Well, what's that? The b goes in, the 1 goes in. What happens to this as b gets large? This gets large. This is infinity. And since this limit is infinity, we say that this integral diverges. And that's the way it goes. If you're looking to practice, and I know you are, you want to know how to do this thing, and you want to know how to do this thing. Oh, I'm sorry. I'm going to grab the eraser. Ooh, how do you handle those? Golly, that's a technique of integration we should be familiar with. That's a technique of integration we should be familiar with. I will let you play. This is an example of a different sort. The integral from 0 to 9 of 1 over radical x dx. Well, what happens with that? 1 over radical x looks like this. You're looking to go from 0 to 9. You want this. But you can't go to 0 because there's an asymptote there. So instead, you go to some number a, and you push a towards 0. you take the limit as a approaches 0 of the integral from a to 9 of 1 over root x. Again, it's the same kind of idea. I can't get to 0 because of that asymptote, but I can go to a and I can push a. And so that's what we do. It's a limit as a approaches 0 from the right. So we take the limit as a approaches 0 from the right of antiderivative from a to 9. How do we do that? The 9 goes in, the a goes in. What happens to this as a goes to 0? As a goes to 0, this drops out, and you're left with 6. Similarly, the integral from 0 to 1 of 1 over x dx. To be clear, this is 1 over x. There's 1. Looking for this area. Can't get there because of the asymptote. But you can go to a and push a, and that's what we do. We take a limit as a goes to 0 from the right of the integral from a to 1 of 1 over x dx. How do we do that? We find an antiderivative from a to 1. The 1 goes in, the a goes in, and we ask what happens as a approaches 0 from the right. And it turns out that that blows up. And since that blows up, this integral diverges. This would be more on your own. You should know how to do this. The thing to think about. There are only two kinds of improper integrals. They are both demonstrated in this video. One of them is the kind of integral where we push a toward an asymptote. The other is the kind of integral where we push b toward infinity. But those are the only kinds there are, and so I think you can handle this. And our time is up.